Assalamualaikum warahmatullahi wabarakatuh. I am Nur Shakira Umaira binti Muhammad Ismail with student ID 2020-883344.
My name is Aina Zafira binti Azman. Student ID 2020852486.
Hi, my name is Nur Aisyah binti Muhammad Syaiz and my student ID is 2020611458.
And we want to present our video about related rates, which is one of the application of differentiation. In differential calculus, related rates problems involve identify a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are known. The rate of change is commonly with respect to time. The methods of related rates have broad application in these fields as science and engineering often relate quantities to each other. Since most problems involve several variables, differentiation with respect to time or one of the other variables requires application of the chain rule. Essentially, if a function capital F is defined such that capital F equals to f of x, then the derivative of the function capital F can be taken with respect to another variable. We assume x is a function of t, that is, x equals to g of t. Then, capital F equals to f g of t. Hence, capital F prime equals to f prime g of t multiplied with g prime of t. Written in Leibniz notation, this is d capital F over dt equals to df over dx multiplied with dx over dt. Thus, if it is known how x changes with respect to t, then we know how f changes with respect to t and vice versa. We can extend this application of the chain rule with sum, difference, product, and quotient rules of calculus and the rest. For example, if f of x equals to g of y plus h of z, then df over dx multiplies with dx over dt equals to dg over dy multiplies with dy over dt plus dh over dz multiplies with dz over dt.
Now, I will talk about the most common way to approach related rates problems. First, identify the known variables, including rates of change and the rate of change that is to be found. Draw a picture to represent the problem because it can help to keep everything in order. Second, construct an equation. The equation must relate the quantities whose rates of change are known to the quantity whose rate of change is to be found. Third, differentiate. Differentiate both sides of the equation with respect to time or other rate of change. Often, the chain rule is employed at this step. Fourth, substitute the known rates of change and the known quantities in the equation. Solve the wanted rate of change. Errors in this procedure are often caused by plugging in the known values of the variables before rather than after, finding the derivatives with respect to time. Doing so will yield an incorrect result, since those values are substitutes for the variables. Before differentiation, those variables will become constant, and when the equation is differentiated, zeros appear in the places of all variables for which the values was plugged in.
Leaning ladder example. A 20-meter ladder is leaning against the wall of a building and the base of the ladder is sliding away from the building at a rate of 3 meters per second. How fast is the top of the ladder sliding down the wall when the base of the ladder is 8 meters from the wall? The distance between the base of the ladder and the wall x and height of the ladder on the wall y represent the sides of a right triangle with the ladder as the hypotenuse h. The objective is to find dy over dt, the rate of change of y with respect to time t, when h, x and dx over dt, the rate of change of x, are known. So, step 1, what we need to do is we write what we know. We know that x equals to 8, and then height h equals to 20 because the 20-meter ladder, and then dx over dt equals to 3 because the base of the ladder is sliding away from the building at a rate of 3 meters per second. And then we also know that dh over dt is equal to 0. Then dy, what we need to find is dy over dt. Step 2, we need to write from the Pythagorean theorem the equation x squared plus y squared equals to h squared. Then describes the relationship between x, y, and h for a right triangle. Differentiating both sides of this equation with respect to time, t yields d over dt x squared plus y squared is equal to d over dt h squared. Step 3, when solved for the wanted rate of change, dy over dt gives us d over dt x squared plus y squared equals to d over dt h squared. d over dt x squared and plus d over dt y squared, we split this, equals to d over dt h squared. And then we differentiate x squared to x dx over dt plus 2y dy over dt, we differentiate y squared to equals to 2h dh over dt. X dx over dt plus y dy over dt equals to h dh over dt, and then dy over dt, we must dy over dt equals to h dh over dt minus x dx over dt over y. We put dy over dt in one side and the others on the other side. Step 4 and 5, using the variables from step 1 gives us dy over dt equals to h dh over dt minus x dx over dt, all divided by 5. dy over dt, we plug in the number, h equals to 20, dh over dt is equals to 0, x equals to 8, and dx over dt equals to 3. So 20 multiplied with 0 minus 8 times 3 over y equals to negative 24 over y. Solving for y using the Pythagorean theorem gives us x squared plus y squared equals to h squared. 8 squared plus y squared equals to 20 squared because x is equal to 8 and h equals to 20. So we just plug in the number. Y equals to 4 square root 21. So we plug in 4 square root 21 for the equation. Negative 24 over y equals to negative 24 over negative 24 over 4 square root 21, and then equals to negative 2 square root 21 over 7. It is generally assumed that negative values represent the downward direction. In doing such, the top of the ladder is sliding down the wall at a rate of 2 square root 21 over 7. Okay, that's all from me. Thank you.
In conclusion, in each problem, we identify what we were given and what we wanted to find. We next wrote down a relationship between all the various quantities and used implicit differentiation to arrive at a relationship between the various derivatives in the problem. Finally, we plug the known quantities into the equation to find the value we were after. That's all from us. Thank you.